So we will be starting in next 2 3 minutes. We will wait for students to join.
right? And then we will be discussing some of the portion that we have covered in the classes, and then we will solve the questions. Okay, so we'll start the session. So, good evening, everyone. I'm Prashil. I'm a Prime Minister's Research Fellow at IIT Mumbai, and here we are learning advanced thermodynamics and molecular simulations. So, this is an advanced course where we are learning some of the techniques that will be used to study the system in computer. Right, that's why the term molecular simulation is there, which will start in coming weeks. Right, so I'll just briefly recap what we have studied so far so that it will be easier for you to uh, summarize and work upon. Okay, so this is 8 live interaction session. So we know that we are studying thermodynamics, and in throughout this course we have started learning about thermodynamics, right? So thermodynamics, right? And here we are representing the terms that we have used in the undergraduate thermodynamics using some mathematical representation, right? Or we could say physics based framework. Understand systems at molecular length and time scale. Right, now I'll just give you an example. For example, I have a bottle. In this bottle I have a chemical. This is containing a chemical, right? So what is happening? The volume of the system is constant. So this is my system to be studied, right? And rest of the things which are in the vicinity or away from, right, is the surrounding, is something surroundings, right? So this is our system, which is a bottle, right? And that's where the system has volume V. There are some water molecules, and over this there is some air. That is, number of particles are constant. They are not being exchanged with the surrounding, or they are not transferred in the surrounding, right? So number of molecules are also constant. And since this is an experiment which is carried out at some temperature, for example, I'm keeping this water bottle or a chemical bottle at room temperature, so temperature is also constant. So this is my NVT symbol, which we used to refer to as closed system. We used to refer to it as closed system, right? With rigid wall. So depending on the type of the wall that you have, you can have constant volume system or constant pressure system, correct? So this is NVT. And now I'm saying, for this system, right, there is some process that is happening, right? Inside, some process is happening. I want to study what are its equilibrium properties. So what I need to do for that, we need to First of all, create this system on computer, use mathematics to represent the surrounding, right, and the system, and then we are allowing the system to evolve. Again, it is similar to, I have a system, I'm keeping it at some temperature, pressure, room temperature and conditions, right? And and what I'm doing, I'm observing the system, what is happening, right? So here I have a qualitative information, what is happening, number of molecules are constant, volume is constant, temperature is constant. But I can also quantitatively calculate, okay, how these molecules are moving, what are their velocities, how they are distributed, are their molecules near the surface or not, those sort of things I can calculate, right? So every instance there is some change that is happening, and I'm taking multiple snapshots of how system is evolving and then calculating the average properties. For example, density, or if these molecules are adsorbed at particular angle or something, then we can calculate angle distribution and various other properties. Using equations we can also call using equations for energy we can also calculate various properties, for example surface tension, interfacial tension, and many other properties. In fact, if I am having a solid material, then I can also calculate its mechanical properties, elastic modulus, etc., right? So this is all thing that is possible here. And for that we need to calculate something called as q. Q is called as partition function, right? Partition functions, which is given as summation of ei. So ei is the energy of a particular microstate, right? Particular snapshot, which is dependent on the position of the particle, and position is represented as x, right, and momentum, that is the what is the velocity. So this gives you the potential energy, whereas this momentum will contribute to kinetic energy. So there is potential energy and kinetic energy, correct? Potential energy and kinetic energy. So this together will give you the total energy, which is also called as Hamiltonian. H stands for Hamiltonian. Hamiltonian, correct? So this is how it is. Now what is the point of getting Q? Because we have derived for a particular ensemble, this partition function is defined, and this partition function is then related to something called as free energy. Free energy, right? So you know that free energy, it is defined for a particular ensemble. For example, here if we are studying NVT system, which is also called as canonical system, or in BTech we have studied, it's also called as a closed system with rigid wall. For that particular system, we know how it is related to NVT, right? So if I get this energy for a particular microstate, I'll sum it over all the possible microstates that are possible and which are in real life are equal to infinity, right? But then we can take some sample of that, and then we can calculate the q, and once we are getting the q, q can be helped, q can be used to get the free energy f. Free energy f. correct? And generally what we get, we calculate something called as delta F. So this is free energy at a particular state. We calculate what is called as delta F. F1 is a value at a particular, so this is a reference value. Instead I should write Fr minus reference, correct? Minus reference. Delta F. Again, to give you one example, which is advanced part, yes, but then I'm just giving you a hint how it can be used to get some property. Reference value, and this is a particular point which is varying. So this is the distance, so I'll get theta, and this is my delta F. So I already have this reference considered. That's why you can see free energy profile like this. And this QNVT sometimes is represented as rho at that point divided by rho bulk. Rho at that point divided by rho bulk. This is local density divided by bulk density. Local density divided by bulk density. This tells you what is the probability of molecule to exist at I compared to reference. If the probability is high, that means at that point this free energy value will be negative, and that's why more the probability, more the negative value will be, and that's why it is more favorable state. More favorable state. So here what I'm saying, I'm considering for example a surface. I have multiple polymers and I want to see which polymer to be coated on a surface. So what I calculate what is the free energy change. So this is what is delta F, free energy change with respect to reference. So if I consider molecule here far away from the surface, that is the reference. I'm subtracting that from every value, so I'm going to get delta F, and I'm calculating what is the free energy value, right? Using this equation kBT, this, correct? So it will be kBT, that is temperature is constant. It is what? Ln of ln of at local point minus it is plus kbt reference. So I'll be having minus kbt common, right? This will be ln of ln of at I divided by q and vt at reference. Right, similar sort of system we can get. So we always calculate something called as difference in the property rather than calculating the absolute value. Now this reaction coordinate zeta, this can be anything. For example, here I am considering what is the distance between a polymer and a surface as the zeta. This zeta can also be phi, just like what we have seen in the mixing and separation problem, right? So I have two mixtures, two phases. There will be phi 1 here, phi 2 will be here concentration, and in this phi 1 phase there will be some x1 concentration and x2 concentration of other component will be. So this here, for example, phi 1 is dominating, then this is limiting, x2 will be dominating, then this is limiting, right? So in each of the phase other component is also present, but that is present in the limited value. And these things, for example, if I am considering only phi 1 as a reference, so I'll just vary phi 1, phi 2 will be automatically varied, right? Because those are related. So if I change the value of phi and I'll calculate free energy density just like we had seen in previous classes, F versus phi, and you see that the graph might look like this. So F versus phi, if the graph looks like this, that means what happens, and here these are the initial values phi 1 and phi 2. So what is happening in both the cases, at this point also and this point also, the value is higher than what is the equilibrium value. So both will go here and here. So what is happening? In this case, mixing will be favored. Why mixing will be favored? Because here you can see f of phi at particular value, and this is f of b. Correct? This is at f of b. So this is less than f of beta, and that's why system will always try to go from here to the local value where there is a minima. Right? So what will happen? The phi 1 and phi 2 value will change, and it will go to match this value of phi, right? So for example, I'm saying phi is equals to x plus 1 minus of x or something similar, right? So these are the contributions. Some weighing factor will be there, some weighing factor will be there. That weighting factor will decide. Okay, similarly in other case, so in this case mixing will happen because you know the free energy value here and free energy of the solution is here, right? So obviously it is going to go, because rate is something that is given by f dash. So phi will tell you the current value, current free energy at a particular phi. F dash of phi will tell you rate of change of this, right? If there is a rate, obviously it is going to get at the minimum value where f of phi, f dash of phi is equal to 0. Until that rate equals, there will be continuous transfer. So it is a free energy that tells you okay whether the mixing or the separation will happen. This is case 1, right? I hope this is clear to you, and this has been discussed extensively in the class. So if you go through those class lectures and then look after the videos over here, it will be helpful for you. So it is a case of mixing. Let me know if there are any doubts. So this is case 1. Where we see how F, that is what is the Helmholtz free energy density, is varying with respect to the phi is called as the concentration of the solute, right? With respect to the concentration, how free energy is varying, and it tells you if you increase the solute concentration, whether the mixing is favorable, whether you decrease, what is the value, right? Similarly, there is case 2, where you can find that again F is a function of phi, and in this case you will see curve like this. This is the curve, and in this curve you can find that these are the starting points. If phi 1 and phi 2, these are the concentration of solute and solvent if I want to consider. So if I start from any point, suppose I am starting from this point phi 1, you can see almost the free energy decreases here and it becomes value over here, right? So it becomes minimum over here. So what is happening, if I start with this phi value, obviously it is going to end at this position. So here the free energy is minimal. That means here the concentration of solute, here it increases, right? it increases. That means if this was the mixed state, this mixed state is going to get into, because this is what is 5b, f of 5b, right? So this is f of 5b, and this is my f of 5, correct? So you can see f of 5b is greater than f of 5, correct? So in this case, sorry, the case is opposite. This is the value f of 5, this is f of 5, and this is 5b, correct? 5b, so it is going to get down to this point, right? So f of 5b is lesser than f of 5, correct? So this is my f of 5, this is f of 5b. So that means there will be separation, this system will go from this location to this location. So this is how we can define mixing and the separation. Then there is third case called as case 3. Here it is like I have multiple maxima and minima. So in some case we can say it will go here if I start from here. If I start from here, it may go here, right? Similarly, if I start from here, it will go here. So it is a mixed case where it has combination of multiple maxima and minima location. Maxima and minima locations. So in that case, we need to find what is the equation, and accordingly we can say at particular value, if I start from this, what will happen? If I start from this point, what will happen? If I start from this, what will happen? Again, interesting thing I wanted to showcase. Okay, that I'll explain later on upon solving the questions. So here are some of the questions of the assignment. The first question is phase space is defined as. So you should be aware of what is the phase space, right? What we defined over here, we defined something called as F, Helmholtz free energy density. Helmholtz free energy density, and this is related to phi. Helmholtz free energy density is related to phi. So from the phi, that is what is the distribution of energy or distribution of states into the system. For example, I have a NVE system. How energy is distributed, we need to look after. For NVT systems, I need to see how energy is distributed. NV also energy is constant, but its distribution among the particle is different. So the distribution of energies in different particles, or distribution of energy in different microstates, right? In this state, NVT will give you the phi is related to Helmholtz free energy, and we know that Helmholtz free energy is related to multiple other phenomena that we see. Everything that is happening is because of the free energy value. So this free energy value calculation has two parts, or two ways in which we can calculate. One is, there are two ways in which we can calculate this. The first way that we have is using toy models. just like lattice Boltzmann model or ideal gas equations that can be used to study the property. These are the toy models which do not exist in real life, but then they are giving us a prediction, predictive power to visualize what can happen, right? What can happen. So predictive powers can be obtained. And there is something called as molecular simulations. For that molecular simulations, we know particles are moving in the phase, right? This is my system has number of particles and these are moving. So each of the particle is having some position xi and it has some momentum pi, correct? Position is there and momenta is there, and similarly there are n such particles are there. So each particle's momentum and position is changing, right? So for example, I have only one particle. I can see how x is changing. Then on other axis I can see how momenta is changing. This is the graph. So this is for one particle I am having two coordinate axes. Similarly, if I am having positions in y and z direction, then it will be like 6, right? And how this 6 comes? 3 dimension into two particles. No, 3 dimensions into two is one is momenta, other is position. So these are the 6 variables which are varying. So it is 6, right? It is 6, and this is for one particle. Similarly, for n particles, it is 6n dimensional space. 6n dimensional 6n dimensional space, that is a phase space we call. So what is that phase space mean? It is not the volume of the system, so it is cancelled. All the possible values of position and momenta of molecules, yes, so this is correct. This is something that is position and momenta, how it is evolving for each particle, right? Distinct phases present in the system, no, this is not referred to. It is defined as all the possible values of position and momenta, and then we are plotting that in 6n dimensional space, and that will give you the phase space, right? It will give you the phase space. Correct. No, there is second question which is on your screen about lattice model, which we have covered in the class. What were the assumptions that we made? These are given and we need to identify which is not assumed in the lattice model. So please let me know what is the answer to this question. So there is question number 2. So when we solve the toy model, that is lattice model, to understand how mixing and separation can be defined, right? There is solvent, particle, solvent, solvent, solid, solid interactions, right? And then we got, okay, what is the chi parameters that was used. So lattice model, this is a simple model that defines what happens in the solid and solvent system, right? And there we assume that, okay, interactions, okay, exist between nearest neighbor, that is true. This is my lattice, and we see that there are multiple lattice positions where these molecules can go and absorb. Some of them are occupied by the solvent, some of them are occupied by the solute, right? And likewise, so all the sites will be occupied, but then there is solo solvent distribution. So we can assume that, okay, that the interaction will be there only with the neighbor molecules, right? So this guy can interact with its neighbor like this. Only nearest neighbor interactions are possible. That's why interaction exists between neighbors. The interaction may not be with the molecule here, which is away from, which is two cells away, right? It's not there. So nearest neighbor is something that is interacting, and then cell volume is same as the solvent volume, correct? So this is the volume of the cell, which is equals to the volume of solvent, which is equals to volume of solute, and which is equals to volume of cell. So this is also correct. Then all cells are occupied either by solute or the solvent that I already have defined. So this is what is there, and configuration of system cannot change. Is it true? And we are saying what we see in the lattice model, these positions are being exchanged, right? Solute solvent positions are changing. So what we see over here is the configuration of the system is changing, right? And which is what is not true. Here it is saying that configuration of the system should not change, which is not true, and hence this is wrong. So it has been asked which is not typically assumed in the lattice model. So this is not assumed in the lattice model, correct? And there is a question number 3 on your screen. Try to solve this. This also we have assumed in the class, right? While deriving the equations. Solute solvent interactions, right? How to define those numbers. So what is the value? Average number of solvent solvent contacts. So we calculated solute contact, solvent contact, and solvent contact. So average number of solvent solvent contact for lattice model of Z neighbor sites, right? Ns is the number of solute, and phi is the fraction of the solute. Phi is the fraction of solute. Fraction of solute. So here we calculated, okay, we were having Ns number of solute site divided by Ns plus Np. S stands for solvent, okay, S stands for solvent, P stands for solute, correct? So solvent or solute both are equal. How did we calculate? This is what is giving us the fraction of solvent contacts or solute contacts, right? This has to be multiplied with the coordination number, right? If the number of solute molecules are higher, or right, then the number of contacts will also be higher, so coordination has to be multiplied with ns, right? This we have calculated for one solute, we have to calculate for all solute or all solvent when we are considering either of them, solute or solvent, right? And when we calculate for one solute, other solvent, when we calculate for one solute, for example this is one, we are calculating for one, and we are also calculating for two, but number of contacts are how many? Only one is there, right? That's why we have to divide by the multiplicity. Pairwise interaction multiplicity is 2. This is how it is, and then this is my phi, this is my phi. So what is the answer then? Ns by 2 into phi into z. Ns by 2 into phi into z. This is for solvent, this is for solute, so 1 minus of phi will be occupied by solvent. Option D is correct. Option D is correct. Solvent. Again, this has also been discussed in the class, right? So question 3 is done. Calculated how many sites will be there, right? Average number of solvent contacts that we have calculated. Then for the canonical partition function, lattice model again given, Mill field approximation is then, that means the energy of system is equals to ei, which is equals to summation of all possible energy for all state that are there, right? So this is value divided by total number of states that are there. So we are taking an average value instead of doing it for all the configurations, and using mean field approximation what we see is exponential minus of ei divided by kbt. This is the interaction energy divided by kbt, and an exponential, this is the value for a particular state, right? Particular state. Instead that we'll just assume it as average value divided by kbt into into w is the number of states, number of possible configurations that are there, right? So this is how it is. Canonical partition function is equals to w into exponential minus, it should be minus average value divided by kbt. So this is the answer. So to question number 4, answer is option number 2. Answer is option number 2. Using mean field approximation we solved this in class. The solvent quality parameter chi, very well known. This has been discussed multiple time in the class, right? This value has to be a negative value, right? It is something called as chemical compatibility. So it has to be a negative value, right? Only one option is there with the negative. This is what is the answer to the question. Now this was replaced with this. Why? There were two reasons, right? There were two reasons we discussed in the class why it was replaced. Please let me know what were the results. I'm here. We can discuss more about this in detail. So question number 6. So we replaced this thing, right? We made some assumptions while solving the and equation and deriving the lattice Boltzmann, not lattice Boltzmann, it's lattice model, right? For mixing and separation. First reason was resulting free energy density should be symmetric about 5 by 2. 5 is equal to 1 by 2. That value was there and it should be symmetric. It should be symmetric, and that's why we have replaced this. And second thing is, when you draw a common tangent of resulting free energy density has a slope equal to 0. So these two reasons were there that we consider these things, right? We consider these things in the lattice model of solutions. So these were the two approximations. Volume fraction phi c at critical point, right? Volume fraction, what was that value? You know, at critical point what we did, we had multiple regions, right? So f of as a function of phi was there. The first derivative will give you the binodal points, second derivative will give you the spinodal points, and third derivative will give you critical point. So that you have to take multiple time derivative, and we got one answer. That what was that? Phi plus phi minus of 1 is equals to 0, correct? So what is the value? Phi 2 phi, this is from second derivative, correct? So phi is equals to half. So this is what we got at the critical point. At the critical point, the value was equals to 5 by phi is equals to 1 by 2, and when you substitute this value 5 by 2, you will get mixing. For that mixing, we know that there was a relationship. One was we observed 1 minus 1 divided by 1 minus of 5 minus 1 divided by 5. This was the equation we obtained, right? You just need to substitute this value here, and you will get here the mixing will happen. The mixing will happen with chi parameter, it is asking, right? Upon substituting, we were getting this value 5 minus of 1. I'll write it again. Minus of 5 minus of 1 minus of 2 chi equals to 0. Here you just need to substitute that value, and you will get that when chi is less than 2, this sort of graphs were there, right? If you remember, complete mixing, then on the verge of mixing, and then there was separation like this. There was separation. So complete mixing, chi equal to 2, this was the case. Chi greater than 2 and chi less than 2 was like right? Like this separation. Correct. So for chi less than 2, mixing will be always be there. Chi less than 2, mixing will be always there. This we have already proved. That's why I am not going to the details, right? Now, solution to the Newton's law of motion for molecules in the system is the basis for what we do in the molecular dynamics simulation. We have the position of the particle, right? We solve Newton's equation, force is equals to mass into the acceleration, which is equals to force d2x divided by d2 is equals to force, right? And this acceleration value we substitute back. So we calculate the energy, we calculate the force, and then we know position at t plus delta t is equals to position at t plus velocity into t, right? The equations, right? Similar to this, we get multiple algorithms. So what we do there, using Newton's equation, we calculate the value of force by mass, which is equals to acceleration. We substitute back to get the position. So right, new positions and new velocity. So this is my acceleration. So what we are doing, we are using Newton's equation, Newton's law of motion, right, in molecular dynamics simulation, which is not the case for Monte Carlo. Here we use something called as metropolis algorithm. Metropolis algorithm. So question number 10 is on your screen, and I already shown you. Okay, F is equals to derivative of energy dE by d x. X is my configurational coordinate, minus of this value, and this is called as grad. So F is equals to minus of grad delta u. This is what is delta u. Delta is my potential, so gradient of potential is equals to force. Again, simplest thing what I am telling you, if I am having a curve like this, if I want to get area under the curve, I'll divide this into small fractions, right, and I'll sum it up to that value. So as I move, I'm integrating the curve. So this integration, this is called as function, and integration will give you the area. So and derivative of this area will give you the function. That is what is back and forth calculation. So integrate. So we have the force, we just integrate it. We are going to get what is called as energy, that is potential. And when we take the derivative at different locations, we are going to get what is called as a function. So I have a function, I get area. If I have area, I get a function back and forth. Correct? Integration of any function will give you the area. This is what about the live interaction session. Please let me know if there are any doubts. I'm here to solve the questions. So if there are no more doubts, we can close the session and we will meet in the next coming live interaction session. Thank you.